Welcome to Honey of Knowledge. Today we will be talking about the application of concave functions in total active coronavirus infections and finding its peak number. If we take A as the active cases, I as the infections or total number of infections, R as the recoveries, which includes the number of dead people, unfortunately. So we can say that active cases A is equal to total infected minus total recovery. So if we want to know how active cases is changing, we can say dA upon dt is equal to di upon dt minus dr upon dt. Now, if we want the active cases to stop growing, this needs to be 0, which implies total number of infection must grow at the same rate as total recoveries. Now, this is not the only criterion here. Let's understand why. Let's suppose at a certain point of time, total number of infection is growing at the same rate as total number of recovery. But it may so happen that at the next time period, this thing could increase. So this would become positive. So we want this thing to decrease after this stage. So we want first this and di upon dt should be less than dr upon dt in the next period. So to recap, if A is the total number of active infections, I is the total number of infections, R is the total number of recoveries, which includes deaths, we can take a first order differentiation with respect to time to get the rate of change in active cases. And if this is equal to 0, we can say that the active cases have stopped growing, and we can say this is peak of total active cases. Now, if we simplify this, we get this, which implies that total number of infection is growing at the same rate as total number of recoveries. Now, this is not the only criterion, because it may so happen that at the next time period, total number of infections could grow at a higher rate than total number of recoveries. So what we desire is that total number of infection should now come down, which means that the increase in total number of infection should be lesser than the rate of increase in recoveries. To rephrase that, the rate of increase in total infection should be less than the rate of recoveries in the next period. Now, let's understand this thing graphically by taking A as the example. The shape of A can be of various kinds. A can increase like this, A can increase like this, or A can be like this. So if A is like this, total active cases is continuously growing. If A is like this, total active cases is again growing. But if A is like this, my total active cases is increasing but reaching a peak over here and then falling down. Now this kind of a graph or shape is known as concave function, or you can say a concave kind of a growth. So we need a concave kind of a growth. So let's understand what is the meaning of concave kind of a growth. This is your total active cases. This is your time. Now, how do I interpret this kind of a shape? At any point, I can draw a tangent, which is the slope. I can draw a tangent here. I can draw a tangent here. Similarly, I can draw a tangent here and here. Now, if you look at this, the steepness over here is like this. Then it's like this. Then it becomes flat. Then it is downward sloping. Downward sloping. If you look at a pattern over here, the steepness is falling from upward to flat to downward. Now this is known as your concave kind of a growth or concave function. Now if steepness is falling, what do we know about steepness? Steepness is essentially dA upon dt, or the slope. So dA upon dt is falling, which implies d upon dt of dA upon dt is less than 0. And we can write this guy as d2a upon dt2 as less than 0. So this is the idea of a concave growth or concave function. d2a upon dt2 is less than 0, or the slope is falling, or the rate of increase in A is falling, or the rate of change in A is falling. So essentially, if we look at A is equal to I minus R. If I look at this side, dA upon dt is equal to di upon dt minus dr upon dt. So if dA upon dt is falling, di upon dt minus dr upon dt should fall. So let's look at this part of the equation. Now, dA upon dt is equal to di upon dt minus dr upon dt. Now this guy over here needs to fall. So this guy over here needs to fall. If this has to fall, this thing has to increase at a slower rate, which means di upon dt ddt should be less than ddt of dr upon dt. Now if we look at an approximation of this, this is nothing but increase in daily infections should be less than increase in daily recoveries. Now what kind of a data would support this? Now if small I is your daily infection, I'm taking small I because capital I is total infection, and small r is your daily recovery. So if at some point I have this equal to 4500 and then it goes on to 5000, and so in the same period the recoveries go from 4000 to 5000. Now this kind of data would give rise to this, because at this juncture this thing over here becomes 0, and if you look at the set of these two numbers or these two rows, you would get this. Now this gives you an idea that when can you say that you are near the peak of total active infections. If today's infections and recoveries are the same and previous day's infections is greater than the recovery, then you can say that these two conditions are satisfied and we have a concave kind of a growth and we have reached the peak of the concave growth. I hope you found the video useful. If you liked it, please give it a thumbs up, comment about your feedback, and don't forget to subscribe to this channel for more videos like this in future.